Okay, then thanks for the invitation to the organizers. It's great to be here. It's really a wonderful place. And yeah, after a very nice talk by Christian Listert this morning, introducing you to atomic clocks, he mentioned both the neutral lattice clocks and the ion clocks, and explaining a lot about the blackbody radiation shift. Also, Eckhart now gave a nice historical overview of how it introduced the definition of our SI second nowadays. I take the opportunity now to go more into detail. I was asked to talk about our indium and terbium ion clock, and that's actually a very new clock. I would say we only call ourselves a clock since last year, 2022. So this is something really new on the market. And I take now the opportunity to show you a little bit how this multi-ion clock works and what blackbody radiation means there and how we aim to measure it more precisely, the Stark shifts. So our group is called actually Quantum Clocks and Complex Systems. We're located here at the Gebert-Meyer building. We also have always nice exchange with Osaka and Tokyo University. So if you come to Braunschweig, please visit us. And we have in total 4 different teams. Today I will mainly talk about this here. But of course, ion traps are very important, and we also benchmark now ion traps for industry, for the quantum processor, for quantum sensors. So we do a lot of technology transfer, but I will not touch much on that today, don't worry. We also study topological defect, transport in these complex systems with long-range interactions. We search for new physics, new bosons, test local Lorentz invariants with precision spectroscopy in ytterbium. So all this you can see at PTB. But today I will focus exclusively now on the indium ion in combination with ytterbium. It's a dual species atomic clock. So optical clocks with trapped ions have been mentioned this morning and also by Eckhart now. You have seen this funny kind of constructs. These are the ion traps, the classical Paul traps, a 3D trap where exactly at one sweet spot you can localize and very precisely trap a single ion. But then, as Eckhart mentioned, the stability is an issue. The signal to noise, you can imagine this qubit is either 0 or 1, and you need a lot of statistics to average down and to get a good sensitivity. On the positive side, I mean, these ion traps are perfect harmonic oscillators. Yeah, so you can do really beautiful Chaynes-Cummings physics there. And you can cool the ion down to the quantum mechanical ground state where the wave function has something like 10 nanometers spread only. So we know where our quantum particle sits within something like 10 nanometer precision. And that gives this enormous this enormous accuracy that is achieved nowadays, which is actually the best ion clock worldwide, is just hitting barely now the 10 to minus 19. Yeah, this is thanks to the strong localization, knowing exactly at that point how do the electric and magnetic fields look like, what's the quantum state of motion. And I should also say, contrary to the lattice clocks, where you have to be sure that you're sitting at this magic wavelength that Christian explained today, here we only have to make sure we're sitting at the minimum of our harmonic oscillator, because here the electric field vanishes and we don't have any first order shifts. So that's a bit easier. And then there are many, many other nice things. In particular, I should point out that one. If you work with ions, if you rip off an electron from the atom, many of the transitions are shifted into ultraviolet or blue. So you can imagine the black body radiation shifts are very low for many ion species. I mean, I'm saying for many, not for all. You always have to be very selective if there's a higher lying state shifting it. But most of the ions are doing pretty well. Well, now I was talking about the accuracy and 10 to minus 19, wonderful. But how about the resolution? Because if you do a measurement, there's always noise. Yeah, everyone who has done a graduate lab, you see noise in the beginning. So that means I need to do a lot of statistics to resolve the signal out of this noise. And the statistic in optical clock scales like this. So if you assume wide frequency noise and you do a frequency measurement, then you're scaling down, the resolution improves with a factor square root of tau. Tau is the measurement time, so the longer you measure, the longer you average, you can improve the resolution, the sensitivity of your experiment, but only with the square root of tau. So you can imagine, if you start out here, it can take horrifically long to really break through this magic line of 10 to minus 18 and get to the 10 to minus 19 level. Yeah, it can take you many days, even weeks of measurement if you have this poor short-term stability. So this is at the moment actually limiting the uncertainties of single ion clocks. And we have asked ourselves, how can we improve this? So several years ago, when we started this project at PTB, we had looked at this equation about the sensitivity of such a clock. I mean, the neutral atomic lattice clocks, they profit strongly from this shot noise factor, so classical shot noise, a square root of n. So if you have thousands of atoms, that helps a lot, and you get the same in 1/1000th of the time. That's really linear in the time, as you see. It's both under the square root. And on the other side, you can crank up the quality factor. That means go to higher frequencies, maybe the thorium clock one day, to the pushing to the ultraviolet, extreme ultraviolet, or even the indium clock is not so bad. We're working at 236 nanometer. And the resolved line width, of course. Well, our approach back then when we started was the multi-ion approach. We said we want to first get a handle here, because only if we do multi-ions, if we scale up from a single ion to a trapped Coulomb crystal, if we develop now new methods that allow us to control precisely and measure precisely a many-body quantum system with long-range interaction, such a complex system, and open it for precision spectroscopy, only then we can access all these beautiful new type of clocks, entangled clocks, multi-ensemble clocks. Yeah, we can aim at Heisenberg scaling. We can aim at 1/tau scaling if you have a cascaded clock and phase measurement. So that would be really a complete breakthrough if that works, if we can show and demonstrate that we have a high control of such a complex Coulomb system. And of course, what we're doing now brings us close to quantum simulation and information, as you can imagine. There are people who have then similar problem like us doing quantum metrology. So we proposed that back then, long time ago, 10 years ago in 2012. That was the theory proposal that we're aiming to do an indium-terbium ion clock. And it took a while, but then now it's catching up speed. So there are other groups worldwide starting now multi-ion activities in lutetium ion, calcium ion, aluminum scalable quantum logic has been demonstrated, zinc plus, and also the strontium ion clock combined with the terbium from Martin Steiner, where you had a nice poster yesterday. So yeah, we're waiting for more to come. And so what are the possible atomic candidates? I mean, ions, for those who haven't seen Coulomb crystals yet, it's always nice to show. We are working mainly with a one-dimensional system, because here we get the really ultimate precision of 10 to minus 19 that we want to reach. You can think of high stability measurements with large Coulomb systems, but there the accuracy is debatable. And in general, there's a lot of work to be done to open these guys for precision spectroscopy. So we're staying here for the clock with this one-dimensional Coulomb systems, where we have a typical temperature of 1 millikelvin, close to the Doppler limit. And the question is, so if you put now, as I've shown here, many, many ions next to each other, they're charged particles. So why don't they interact with each other? Yeah, if you bring two charged particles next to each other, don't they see the electric stray field from the other particle? And in fact, they don't, because, I mean, otherwise you would have a force and something would move, right? But if it's a stationary system, what happens? Well, you have the harmonic oscillator from the ion trap, and the two charged particles will deform the potential in such a double well potential and sit again at the minimum, yeah, where the gradient of the potential is 0, so you have no electric field, no electric force, and no shift. So that works. However, the gradient of the electric field, so the curvature of the potential, is not vanishing. So you always do have a gradient. And that can be an issue if you have a quadrupole moment. So you have to look very carefully at the electronic structure of these ion candidates and look at the quadrupole moment. You have to look for something that is rather round and symmetric, ideally an S-shell. Yeah? So there are some good guys. I mean, there are several. I was highlighting now the three ones that we're very familiar with: the aluminum quantum logic clock, our indium clock, and also the ytterbium octopole clock in Eckart's and Martin's lab. That also has a very nice, very shell-protected state, the F whole state, with very low quadrupole moment. So these two guys, this is what we're operating at PTB, in Eckart's lab and in our lab. And you see there you really can dream of putting many charged particles next to each other without having really significant shifts that you can't control. Okay, so let's do this. These are our charged particles in our lab. So we're working with indium as the clock ion. And we're using here this singlet S0 to triplet P0 intercombination line that was already mentioned. So it's really nice, J equals 0 to J equals 0, very well protected. But at the same time, since the indium ion cannot be cooled very nicely, you see this is terribly shifted to the ultraviolet. You can't scatter really photons there. Not yet. I mean, maybe if the thorium laser works, we can also do this. But so our approach was first, in order to get really long, big Coulomb systems that have a lot of chaotic motion, we coupled the indium ion with the terbium ions. And we used the terbium ion for sympathetic cooling of the indium. And what you will also see in a minute is that the terbium ion is also a wonderful clock candidate. Yeah, so we have very narrow quadrupole forbidden lines and octopole forbidden lines that we can also drive. And actually, if we have this terbium ion in situ, in the same ion trap, in the same clock, we can use it as a wonderful sensor to read out many systematics that we could not so easily read out with indium. So it's even a profit if you have a dual species atomic clock, if you combine it, not only for the cooling process, but also for the systematics. And why indium? Many people ask, why are you going for something where you have 230 nanometer, 236 nanometer? It's not so nice to build a laser, rather expensive. But we thought indium can be a first prototype, a first proof of principle demonstrator for a simple multi-ion clock. Why simple? Well, indium has a rather heavy mass. It has 115 atomic units. That means the time dilation shift when an atom is cooled close to the Doppler limit is very low. It's 10 to minus 18 already. So this relativistic time dilation I can control already with simple Doppler cooling. It has a very low blackbody radiation shift. This is the static polarizability, and the dynamic one is calculated by Mariana Safronova. Careful, there's still something like a 10% uncertainty on it. I will come to this later. But nevertheless, it brings us to the 1 times 10 to minus 17 at room temperature, which is really nice. This is one of the lowest blackbody radiation shifts of optical clocks you can find. Then, because we don't have hyperfine structure, we also end up with a very low second order Zeeman shift, orders of magnitude slower than in other clocks. And we have a directly detectable transition on the triplet P1. It's a forbidden intercombination line, but thanks to some level mixing of the triplet back to the singlet system, because it's a heavy relativistic ion, you do get a finite lifetime here, and you can actually scatter photons very efficiently, 360 kilohertz, you can detect directly. So you don't have to do complicated quantum logic and scale it up to 50 ions. So that's why we call it a simple approach. And what we do with the terbium ion in situ, well, because this guy has the very strong scattering rate, 50 times larger, we use it for live measurements of micromotion during clock operation, characterization of B fields, and, as you will see in a minute, sensing of intensity profiles. Well, everything that I show you now has been characterized with the terbium ion because it's the directly accessible part. And I don't want to go into details also for the sake of time. I can't go in detail, but there was a question in the morning about heating rate, for instance, right? So this is a diagram where you see the worldwide ensemble of ion traps. Every dot here is an ion trap, and ion traps have different heating rates depending on the material, surface quality, the distance from the ion to the surface, whether it's cryogenic or not. So this has been summarized here in a function of heating power, the power spectral density, and the electron to ion distance. And you see it's a large scatter, depending how clean your ion trap is. But in principle, you have a scaling that goes roughly with 1 over d to the 4, while other people who have Johnson noise have 1 d to the 2. So it depends what is the source of your noise. And our ion trap is here. So we're doing pretty well in terms of heating because it's a specially designed ion trap for metrology. We don't want to have a lot of heating. We don't have to have increased time dilation. And we also measured electromagnetic fields, micromotion, the heating of the trap itself. I'll show you next slide. So this is, for instance, a picture of the resolved time dilation in a Coulomb crystal at the level of 10 to minus 19. So here you see 14 ions, and this was actually a real crystal. I'm just bad in drawing three-dimensional graphs, but this is a 14 ion crystal, and there you see the micromotion amplitude on the nanometer scale. That bar is a nanometer. That relates then to 10 to minus 19 time dilation shift, and you can resolve it atomically from atom to atom over the whole system, over the whole Coulomb crystal. And in 2019, we were able to characterize for the first time our ion trap with the help of a terbium and measuring all these things like time dilation, heating rates, micromotion, all that. And that allowed us to show a potential accuracy. And I'm saying potential because you really have to build the clock and compare it to others and see what goes wrong in terrible ways, be it the wrong cable or so. But this is the potential limit for our clock. And actually, that's at the 10 to minus 19 level. So being a multi-ion clock, but having an uncertainty, a systematic uncertainty at the 10 to minus 19 level. So that was very encouraging for us. And here, if you look here, because we're at the Blackbody radiation conference, this is now the guy who is actually of concern, because it's still it's the largest contribution, yeah, 1.3 10 to minus 17. And the numbers that are listed here, this is the contribution of the ion trap and of the environment. But, sorry, but the accuracy of the polarizability is not so well known. So there we have to work now, yeah, if you really want to claim an absolute accuracy. So how do we get there? Well, as Eckhart and Christian already told you, you have to look at the environment that is around your ion. So the ion trap. And our ion traps, if you have a multi-ion clock and a scalable clock with multi-ensembles, complex clocks, looks also very complex. So the complex system in our lab is the ion trap. And we engineered it ourselves in the clean room of PTB. We integrate directly PT100 sensors onto the chip ion traps so that you have in situ live readout of the temperature. Depending which ion trap we operate, we have a calibration between 30 and 60 millikelvin of these PT100 sensors. Two pieces, one on the bottom and one on the top. And we also had to, of course, then very carefully characterize this ion trap in terms of thermal environment. So that was a nice paper in 2020 where we did this nice collaboration with the CMI in Prague, doing infrared images of our ion trap. So the first step that we had to do is measuring very precisely the emissivity of the materials so that you know what you will see on your infrared camera. You first have to calibrate that. Then you do finite element simulations of such an ion trap that is driven with thousands of volts. Yeah. Then you get some result and you know how the temperature environment looks at the place of the ions over the ion trap. Then the other question was, do we know the material constants, the conductivity and the heat contact? And that was actually a nice trick that we did. That was, you have two possibilities to heat your ion trap. Either you operate it under regular conditions, you have like 1000 volt RF driving the ion trap. And that can heat, of course, because of dielectric losses. You can also reverse it and you can use the temperature sensor, the PT100 resistor, to send through some DC current and bring in some heating power. And that's even better controlled because it's not a RF heating, it's a DC heating. And you know very well the heat load. So we did both of them and did infrared, calibrated infrared images. And then we compared it to the finite element simulation model to see how well it agrees. And from this comparison, we can directly get the thermal contact in such a stack. So when you build up something, how is really the heat flow through the thermal contacts? Because you have a lot of unknowns in such an ion trap. And yeah, for this was necessary to do extensive studies to really claim then that you have something on the order of a few hundred millikelvin of control. We also checked that the PT100 sensor is really seeing the same like the infrared measurements, that you don't have of RF pickup, any RF voodoo, so that works well. We showed the different heating of the ion traps under different operation frequency. Of course, it scales with the drive, whether you operate at 16 or at 22 megahertz. Okay, thank you. So the higher is your RF frequency on an ion trap, the more you heat dielectrically. But actually for mixed species Coulomb crystals, it's much better to go for a higher frequency, because if you look at the mature parameter and the stability diagram of an ion crystal, it's better to have a higher RF drive. So there were many considerations, and in the end, summarizing, that is now the uncertainty budget for the clock campaign last year, 2022. And here we were taking it very conservative. We said, okay, if we operate at 1200 volt, we have this temperature rise with this error that was carefully characterized. We have maximum gradients, temperature gradients at the chamber of our titanium chamber. And we took the min-max value and give this as the full uncertainty. Yeah, we can do better in the future, we know that. We can really do it better. But even if you take this as the min-max worst case, you end up at an uncertainty of 3 × 10⁻19 for the indium clock. So for us, that was first satisfying. Because we have other problems, and I told you the unknown polarizability, which is unknown to the 10⁻18 level. So we first have to work on this. So how we want to do it, I'll show you quickly now in the last remaining minute. So the idea is we will again use the terbium ion as a sensor inside the Coulomb crystal. So this is the mixed species indium terbium crystal, a photo on our CCD camera. And the idea is, so you have seen that in Christian's talk, that was this heroic measurement on a terbium ion clock where they carefully measured the profile of an infrared laser that is stark shifting the levels, and then to calibrate really and measure with a percent, roughly a few percent uncertainty, the polarizability. Yeah, that was part of this morning's lecture. And you know, the stark shift scales linearly with intensity, but who knows the intensity profile directly seen at the ions? That's the big challenge. So how can we do better? Well, first of all, we are aiming to shine in a 10 milliwatt infrared laser at 1650. There we get 10 to the 15 stark shift, and we can resolve the 1% level in an hour measurement. That's easy. This can be done quickly. The problem is now the intensity profile. And there we had an idea that we will use quench cooling. So the ytterbium ion is quench cooled with the infrared laser at 1650 nanometer. And for the theorists, this is basically a 3-level scheme where you adiabatically eliminate the upper state. So you couple these two states with a strong infrared laser, and then you drive that, you dress that one, and give it, basically this gets some properties of the upper state, and you have an effective line width. And the effective line width that you get here, that we can also measure, is again a direct linear function of the intensity of this laser at the place of the ion. So that's the nice thing. We can directly sense the intensity. And we have done these lifetime measurements depending on the intensity of the infrared laser, and you can improve that even further. So you can really see how this suddenly, this forbidden transition broadens up and gets an effective line width as a function of the intensity. So what we aim to do in the future, we will use this now as a sensor to measure the line width of this ytterbium ions across the crystal and get the profile of the stark shifting laser. That's the plan. Good, now I'm concluding. I want to show you the state of the art of this novel indium ytterbium clock that is ticking since last year. Everything's preliminary. We had a nice measurement campaign with Paris and Indre Torino in Italy, and also local measurements at PTB with Christian Lister, Nils Huntemann, Eckhard Pike's group. So what we have done first, we have for the first time measured the absolute frequency of the indium clock with a precision of 10 to minus 16. That was limited actually by the cesium fountain. So that's how good you can get with a cesium fountain. But there we could now really narrow down and improve the uncertainties of this absolute frequency much better. And I think there was also a question in the morning, how sure can you be what you measure, that you, when you compare clocks? And this is what typically or frequently happens. So there's one measurement, another measurement, they don't agree, and then you slowly narrow it down. And only the more clock measurements you do, the more trust you get into the clock. But it takes many years. Yeah. And then we did optical to optical ratio measurements. So this is an example of the indium ion clock versus the strontium lattice clock of Christian Listad. And we averaged down last year to the 3 × 10⁻18 resolution in statistics. And what's very promising, we don't see any flicker flow. So it's still going with 1/√² of tau. So that's a good sign that nothing drifts. And in terms of the first error budget ever that we have set up now under real conditions in operation, this is now the error budget with the leading contributions. We end up at 2.4 10⁻18 plus ugly shift 2.6 10⁻18 because of a missing drift correction on a servo error. So this is then the real life uncertainties that limit your life in the lab. If you have a bad DDS that is not properly steering forward and correcting a possible drift of a cavity, then you can quickly end up in such errors. But this can be eliminated. It's not a fundamental problem, but you have to do it. And you have to be sure you're not overlooking anything like that. But yeah, with this, I hope I've convinced you we're on the way down to the 10⁻19. The next step we have to do is second stage cooling to lower the time dilation shift. And we're scaling it up now to several ions and already multi-ion operation, 4 indium ions, 8 ytterbium ions. We have seen now stable and accurate clock operation at the 10⁻17 level. But that will need to be evaluated this year, and we hope to now demonstrate the 10⁻18 and beyond. So with this, I'm at the end of the talk. And yeah, thanks for your attention and thanks for the collaboration.
Well.